solutions here to the practice problems or exercises at the back of our Exploring Exponential Functions note package. All right. So, a few graphing questions here. So I got some graph paper which I'm going to write the solutions on. So we're going to start by looking at question 1. And so let's read it. Let's read it nice and slowly. It says, let A be bigger than B, which is bigger than 1. Okay. So we're asked to sketch the graphs of A to the power of x and B to the power of x. And we're going to use highlighters. So I guess I should have indicated which one will be which with a highlighter. We're going to label the y-intercept. Okay, we're going to label the y-intercept. We're going to use highlighters, and the graph should show the differences between the two functions. All right. So let's see here. A is less than B, pardon me, greater than B, which is greater than 1. This means that both A and B are both bigger than 1. So the bases of these functions are bigger than 1. So examples might be, so this could be an example, like A could be 10, but B could be 2. That would fit. And you can, I would suggest trying to make up some numbers to kind of investigate this sort of writing to help it make sense to you. And so that would mean maybe we might see something like y equals 10 to the power of x versus something like y equals 2 to the power of x. That's just an example, of course. So and that helps us think about how this graph, the y equals a to the power of x, is going to be different than y equals 2 to the power of x. Okay. So we know one thing right off the bat. We know that both of these guys are bigger than 1. And so if we look at our summary of the key ideas, if our base is bigger than 1, we know we're going to have a growth curve. So both of these graphs are going to look like this normal growth curve, which means it has a point here at 0, 1, and it continues growing larger and larger. And the next thing we know is that the larger the value of B, the faster it grows. And Emily, when she was observing patterns, she observed what we might call the counterpart to the statement, which is the nearer to 1 B is, the flatter or less steep the curve. And the reason I think Emily's insight was particularly useful is Emily's axiom here is general, actually. That's true in both cases. Whereas if we sum up one rule for the value of B if we're dealing with growth, or another rule for the value of B with decay, I mean, we just have another, 2 things to maybe memorize. So I actually think it's kind of neat, this idea of it just being flatter if you're closer to 1. All right. So we're not given actual values, so all we know is that so I'll graph my y equals a to the x first. And all I know is that when x is 0, y is 1, because a to the power of 0 is going to be 1 no matter what. A to the power of 0 is going to be 1. And so I know there is the y-intercept at 0, 1. And other than that, I don't know much. I actually know one thing. I know that when x is 1, y is a, because a to the power of 1 is a. So, okay, I know that as well. But other than that, I'm not, like, really going to be fussed with too much detail here. This is our y equals a to the power of x. And when this dries, I'll highlight it yellow. Okay. So how is b going to be different? Well, b is closer to 1. It's going to be less steep. And also, by being not as big, it's going to grow less quickly. Okay, so I'm actually going to use it at green as well, which may not actually show up on here as significantly different. It doesn't really. Oh, no, so b to the power of x. So to make it more obvious, we'll also use a highlighter. I feel like that pink isn't really popping. Let's try this orange. There we go. Okay. So we know it's going to be less steep. And what's interesting is actually, it's not just less steep in this direction. It's also going to be less steep in this direction. It more lackadaisically approaches the horizontal asymptote y equals 0. And that's our y equals b of x. And if we go back to the question, it doesn't mention it, but I think it's a good habit to also draw our horizontal asymptote. That's part of these graphs, so we don't want to forget those guys. I would say that's kind of important. And no good horizontal asymptote goes without labeling itself. So this is a line y equals 0. Okay. Oh, right, highlighters. So, probably going to ruin my highlighters doing this. I'm trying to highlight the black one without ruining it and smudging. Well, it's looking good so far. Alright, oh, no, it's starting to smudge. Okay. And we'll use this orange for this guy. There we go. Okay. So, moving on. So we also know that 0 is less than C, sorry, is less than D, and both of these guys are in between 0 and 1. Okay, I'll highlight that. I'm going to make sure I'm going to use different colors, so I'll use C for this guy, and D, I'll use this orange. Okay. And overall, I know that 0 is less than C, which is less than 1. And so both these guys are between 0 and 1. Okay, so what does that tell us? This tells us that we're going to have exponential decay, in the same way that this one had exponential growth. Okay. So, what do we know? Okay, so that's kind of it. And we know D is bigger than C, and D is closer to 1, so that means it's going to be flatter. And we know these curves are both going to be a decay curve. They're both going to look more like this. The smaller value of B, the faster it's going to decay. So let's start with C. We'll do C first. So we'll do y equals C of x, which I believe I used a yellow highlighter for. Alright. So one thing we still know is true is that C to the power of 0 is 1. So I know when I graph my C curve, I'm going to have a point here at 1. And other than that, I don't really know much, so I'm just going to draw a curve like this. So we know, as a rule, the smaller the value of b, the faster it decays. So the smaller our base value, the faster we're going to decay. So our next graph is going to decay slightly slower in both directions. Okay, that's our curve y equals c of x, and we'll highlight that in a second. Oh, we should probably label the y-intercept. All right, so then we know y equals d to the power of x. So I know that d to the power of 0 is 1, so they're going to share a point there. But this is closer to 1. It's going to be a little bit less steep in general. So maybe it looks something like that. Both of these guys are going to approach an asymptote, which I didn't really emphasize here as much as I'd like. It gets a little too flat for my liking. If I was to draw it again, I would probably draw it with a little bit steeper curve. But these are just sketches. And that's the asymptote y equals 0. Okay, this is our, we'll call this an orange, oh wait, did we use orange? I think we did. Yeah, orange curve for y equals d of x. And then we'll just highlight these guys. So that's this guy here. And the orange one is going to start lower, but actually come a little higher. There we go. A little bit smudgy there on the right. All right. That's it. Okay. So let's move on to question 3. So question 3 asks us to complete the table of values for y equals 4 to the power of x, and we're going to sketch a curve. Okay, so pretty straightforward here. We have when x is 0, y is 4 to the power of 0, which is 1. When x is a half, we have 4 to the power of a half. Oh, interesting. Okay. That means we're going to have 4 to the power of half is the same thing as the square root of 4, which is 2. Okay. Then we're going to have 4 to the power of 1 here, so that's just going to give us 4. 3 halves. Okay, that's interesting. 4 to the power of 3 halves. Well, that's the same thing as saying the square root of 4 cubed. That's our flower power rule that you may remember from grade 10. So that means we have 2 cubed, which is the same thing as 8. 4 to the power of 2 is going to be 16, and 4 to the power of 5 halves. I might need a little bit of blunt instrument. I'll get something more precise. So 4 to the power of 5 halves is the same thing as the square root of 4 raised to a power 5. Now, let's just talk about what to do if we're just not comfortable with converting between fraction exponents and radicals. Well, if you're going into calculus, I would suggest reviewing this concept. If you're not, this is your last math course, you can actually punch into a calculator. 4 to the power of, I like to put brackets around this, but you shouldn't need to if you use the fraction button, and 5 halves. Okay, we're going to keep that there, and we'll come back to it. So the square root of 4 is 2, 2 to the power of 5, that's 32. And it works. Okay. Great, so now we'll sketch this guy. Break out the ruler for this one. We're going to go all the way up to 32, so it's going to be a pretty big graph. I don't know if that's enough. Well, maybe it isn't, you know? It's not the biggest deal to go off the graph on an exponential graph, at least. And I was never going to plot all the points. All right. So, wait. It's more important, maybe, at this point. Can we see the whole graph on... I think I got to zoom out a little bit here. All right, there we go. Even then, all right, that'll have to do. All right, cool. So what do we got? We know that when x is 0, y is 1. All right, so that's our first graph point. X is 0, y is 1. We know when x is a half, y is 2. When x is a half, y is 2. X is 1, y is 4, 1, 4. X is 3 halves, or 1 1/2. Y is 8, so 1 1/2. We get 4, 5. I'm just going to label 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Wait, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And that should help me get some bearings. I might label a few of those. So that's 10, 20, and 30. All right. Okay. So, sorry, 1 1/2 and 8. Okay, so that means an x is 1, 2, 1 1/2. We're going to be here at 8. When x is 2, y is 16. Nope, oops, forgot. And when x is 5 halves, or 2.5, y is 32. So 2 1/2, 2 1/2, we got 32. Okay. So we're really getting a flavor of this exponential growth behavior. It gets really steep really quick. In fact, it doesn't take long to get sort of incomprehensibly steep. Okay, and it's actually going to get pretty close to the x-axis quite quickly. Even, yeah, it's actually probably not unrealistic to draw it that close. And you can test some values like x is -6 to prove it. Got a little asymptote here. That's y equals 0. And maybe I'll label the x-intercept at 0, 1. There we go. That's our graph. This is, oh, you know what? I should draw an arrow. And it's a good habit to label it. Y equals 4 to the power x. All right. Even though there's no other graph that we can confuse it with. All right. So now we get to my favorite question, which is what would happen if we tried to graph the function y equals -2 to the power of x? Well, some really interesting things happen. So let's think about it for a sec. We're going to make a table of values. We're going to just explore this idea. And we'll get it like a pretty even spread. Maybe we'll start with like -4, -2, -1, 0, 1, 2, and 4. And hopefully that sort of gives us a flavor of what happens when we graph this thing. All right, so let's imagine we have x is -4. So we get -2 raised to a power of -4. Oh, wait, boy, this is a little zoomed out for us now. So I'm going to zoom back in. I'm going to zoom in a lot. All right. Okay, so negative exponent means we really have 1 over -2 raised to the power of 4. I really should have included -3. Yeah, I think I'll include -3 actually. -3. -2, -1, 0, 1, 2. And we're going to say that's going to be a 3, and we'll do a 4. Yeah. All right. So it's going to be 1 over -2 raised to the power of 4. Okay. And then what is that going to be? -2 raised to the power of 4. I'm starting to zone it out. Sorry, it's -2 times -2, which is 4. 4 times 4 is, okay, 16. 1/16. Okay, so maybe I'll sketch that point. I know this is just a sketch. And we'll start somewhere. We'll start 1, 2, 3, 4. We know an x is -4. Y is a 16th, so pretty small value. All right. pretty close to the y-axis. So I'll use a red pen here maybe. There we go. That is even maybe a little generous. It probably is a little closer to the y-axis. Okay. So let's see what happens when x is negative 3. So we get negative 2 raised to the power of negative 3. And that's 1 over negative 2 cubed. Now, what's interesting here is now we have an odd exponent instead of an even one. So this negative number is going to oscillate. It's going to turn into negative 2 times negative 2, which is 4, times another negative 2, which is negative 8. So now it isn't going up to 1/8, it's going up to down to negative 1/8. So when x is negative 3, actually we dip below the x-axis. And so that means we're going to have a point here at negative 1/8. Okay, let's see if we can continue this pattern. Okay, we've got x is negative 2, so that's going to say negative 2 raised to the power of negative 2, which is 1 over negative 2 squared, or negative 1/4, pardon me, or 1/4. So when x is negative 2, y is 1/4. All right. So again, we popped above the y-axis. Let's keep going. Getting a little scrunched here. X. So I'm actually just going to write the answer for this one. You can take your time to do it yourself. This would become 1 over negative 1/2. So when x is negative 1, we get negative 1/2. And when x is 0, we still have the point here at 1, because nothing changes there. 0 to negative 2 to the power of 1 is, pardon me, negative 2 to the power of 0 is still 1. And 1 is negative 2. Okay, so that means that when x is 1, y is negative 2. So you can see we're getting some really bizarre sort of oscillation pattern here. And what is going to be really interesting is if we test some values in between here. Like, what happens when you raise something to a fraction power? Well, we saw what happens when we raise something to a fraction power up here, right? It turns into like a square root. But you can't square root negatives. However, you can cube root negatives. So you get into a really interesting question about what's going to happen between, say, 0 and 1. All right, so we're going to finish plotting a few of these points. Let's say we'll do 2, so we got negative 2 to the power of 2, which is 4. Okay, so when x is 2, y is 1, 2, 3, 4. I think we're going to get run out of room pretty quick here. All right, and when x is 3, we got negative 8 and 16. All right. However, even then, that would be fine, except for the fact that we're going to run into some troubles here. Because, say, we can, say, take the odd roots, but not the even roots of these values. So there's going to be a bizarre sort of domain situation going on here. And even if you graph it in Desmos, it'll look like a continuous line, I bet. That's interesting. I wonder what would happen if you graph it in Desmos. So this will be a problem. And so say if x is 1/2, then we get y is equal to negative 2 1/2, square root of negative 2, which is complex. However, if x is 1/3, then, so there's going to be some domain error. X can't be 1/2. It can't be 1/4 either, it turns out. It can be 1/3. It says what number times itself gets you 2. Actually, you don't know what that number is, but I feel like it's probably like 1.2 or something like that. 1.25. Let's just try it. 1.25 times 1.25 times 1.25. Okay, so it's a little bit higher, and actually has to give us negative 2. So I'm going to make it negative 1.2, say. I thought we were pretty close, so I'm going to say no, 1.256 randomly. Or let's just say 5 times negative 1.255 times negative 1.255. Okay, we're getting pretty close. It's something like that. It's like negative, it's like approximately negative 1.25. So when x is a third, y is a negative 1.25. Well, that's interesting. I wasn't expecting a point quite there. I think we're going to get all sorts of bizarre numbers and patterns within here. But this is something you can investigate. Because it's interesting. This is what can be really neat about math, is problems like this. And I think I'm going to leave it there. I could go on for forever. I think there's a lot to examine in this problem. Yeah, I'm going to leave it there. Let me know if you want to talk about that more. I would probably bore you to tears talking about it. Because I don't know, I think the situation is kind of interesting. I think, like, math is interesting. It's the most interesting when it's not something normal, when weird things start happening. And you have to start thinking outside the box. You have to start thinking about odd situations. Anyhow, let me know if you